Okay, we shall begin. So I have one last topic to cover from Chapter 7, and this is Section 7.10, and it's called the Wilcoxon Mann-Whitney spelled with a H, yes. Okay, the Wilcoxon Mann-Whitney test, and this fits in a larger scheme, or just a larger group of hypothesis tests known as nonparametric tests. Okay. So the thing about nonparametric tests is that they do not put any assumptions about the population. Okay, so they do not make any assumptions about the distribution of the population. Oops. Okay, this is in contrast to the t-test, which has certain assumptions about the population, okay, which assumes that we can apply the central limit theorem. To the sampling distribution. Okay, so the t-test, it relies on the t-distribution, which is kind of a relaxed form of the normal distribution, and it all depends on the application of the central limit theorem, which says you take large enough samples from the population and you calculate the mean, you're going to get the normal distribution. Okay, so because we're not putting any assumptions on this, this fits under this category of nonparametric tests. Okay, and so the Wilcoxon Mann-Whitney test, which I'm going to abbreviate as WMW test, can be used in the same situations as the t-test for independent samples. Okay, and so keep in mind the t-test for independent samples. This is, when do we use it? We use it used to compare the means of two populations based on two samples. Okay. The Wilcoxon Mann-Whitney test is used to make comparisons between two populations based on two samples, okay? But we're not making comparisons about the mean of the population just because we're not saying anything about the mean. So technically, the reason why we call them non-parametric tests is because the mean of the population is known as a population parameter. And so non-parametric tests aren't saying anything about parameters of the population.
Okay. Are they talking about skew?
They're talking about just the distribution of values in the population. Just kind of this funny idea of the distribution of values in the population. That's what we're saying. And so, I'll get into what the null and alternative hypothesis for this is going to be. But so at a practical level, so practically speaking, okay, if we can use the t-test, we prefer to use the t-test. Use it over and the primary reason for that is that in general non-parametric tests are less powerful than their parametric counterparts. Do you remember what it means, the power of a test?
1 minus b?
Yeah, okay, so 1 minus beta is the power of the test, but what does that signify? It's the... Okay, all right, well, power is a good thing, right? So power is a good thing. It's the probability that we make the correct conclusion, and that conclusion is to reject the null hypothesis. So a powerful test says, you know, if the null hypothesis is false, I'm going to reject the null hypothesis, okay? You know, very, very often. And if it's not powerful, then we need a lot of data to convince us to reject the null hypothesis. You know, if it's not powerful, we give more benefit of the doubt to the null hypothesis. You know, or you know, I guess I shouldn't say more benefit of the doubt, but it would take a lot more convincing before we reject the null hypothesis. But so we want powerful tests, and in non-parametric tests, we're not putting any assumptions about the population, and so things have to be really stark or unusual for us to make these types of conclusions. Okay. So just in life in general, if you make more assumptions about something, that might make you more efficient at decision making, right? If you assume certain things and you know, little bits of information come based on your assumptions, you might make very efficient decisions. And that's usually good as long as those assumptions are true, okay? But if you make a quick decision based on a bunch of assumptions and those assumptions turn out to be wrong, that decision could also be very incorrect. Okay, and so the other approach would then to say, I'm not going to make any assumptions about anything, and then you would need kind of a lot of evidence before you make a decision. And that might make people frustrated because you know, you're very slow to make these kinds of decisions. And the same concepts apply to non-parametric tests versus parametric tests. Parametric tests, we put assumptions on the data, primarily the central limit theorem, and it makes our tests powerful. And that's good and all, as long as those assumptions are met. But if they're not met, using a parametric test in a situation where you should not use it can lead you to making the wrong decision. Okay? So anyway, so if we can use the t-test, we prefer to use it. But if we should not use the t-test, don't use it, right? So, and if we cannot use the t-test, we can use Wilcoxon Mann-Whitney test, and so the biggest let's see, common situations to use the Wilcoxon Mann-Whitney test. Okay, so generally we have a small sample, and outliers are present in the sample, indicating that the population is not normally distributed. Okay. Because the central limit theorem applies even if the population is not normal, as long as the sample is large, right? So here, here's the exception. You know, small sample meaning n is, you know, less than 25 or something like that. Kind of the rule of thumb. And you've got some outliers in there. And to us, that would then indicate the Wilcoxon Mann-Whitney test should be used. Okay. Okay, so let me just also make a note about non-parametric tests in general. This is the only non-parametric test we're going to cover in this class, and we're going to spend maybe half an hour or so on it. But you can take an entire statistics course or dedicate your life studying non-parametric statistics and how to make conclusions without putting any kind of assumptions on the data and things like that. A lot of Chapter 8 deals with non-parametric tests for parametric tests for paired data and things like that. And so there's all kinds of stuff. This is the only non-parametric test that we will cover. And but it's good to know that this stuff exists, where if you're not quite sure about the population and the distribution that it comes from, you know, maybe you need to use a non-parametric test. Okay, let's get into how to conduct a Wilcoxon Mann-Whitney test. Oh, another thing. So our book uses the Wilcoxon Mann-Whitney test is the Wilcox-Mann-Whitney test is also equivalent to the Wilcoxon rank sum test. And if you take another statistics class, it's probably more likely that they will teach you the Wilcoxon rank sum test. Okay, but mathematically they're equivalent. The process in terms of carrying it, doing it by hand is different. The process is different, and they didn't realize it at the time, but pretty much the math and the reasons why you get the results were actually the same. Okay, so if you learn the Wilcoxon rank sum test, it's the equivalent of the Wilcoxon-Mann-Whitney test. They're both non-parametric tests. R implements the Wilcoxon rank sum test, not the Wilcoxon-Mann-Whitney test. Okay, so Wilcoxon rank sum test is also in R as, I think, Wilcox test.
So if we put it into R, we'd get the same result, but we couldn't use, presumably they have some of the same, they have some data there that we can't use because it doesn't correlate to the...
So you use the same data. Yeah, you use the same data, you just plug it into R, and you're going to get the same result. It does, you know, it only makes a difference if you're doing this by hand, okay? And so, or if you're looking for the particular test statistic, then the test statistic will appear different also. But
that's what I meant. Like if you it spits out a whole bunch of numbers.
Yeah, yeah. But in terms of the result, in terms of whether to reject or not reject, it's the same. Okay, but the book covers the Wilcoxon-Mann-Whitney test, so we will also. And it goes like this. Again, it's non-parametric, so we are not saying anything about parameters in the population. Okay, so our null hypothesis. Let's say we have so we have two samples, right? Two samples of data. Okay, and so the null hypothesis is that the distribution of the population for group 1 is the same as the, I should have written population distribution, I don't know why I wrote, it's the same thing, right? Population distribution for group 2. Okay, so all we're saying is that the distributions of the population are the same. We're not saying anything about the mean or anything like that. And then the alternative hypothesis is that the population distribution of group 1 is shifted, or in other words, you know, produces larger or smaller values shifted from the population distribution of group 2. Okay, and so we'll do the math through an example, okay? Okay, and so in our example, the book says they gathered data from 2 sections of the forest, and they looked at soil respiration data. So I'm not sure how what exactly soil respiration is, but apparently you look at the dirt and you measure how much carbon dioxide it breathes.
It's like fermentation?
I don't know. But we're measuring how much carbon dioxide the soil is breathing, okay? And so the researchers looked at 2 areas of the forest. They looked at an area where there was a lot of growth and an area where there was a gap in the growth, okay? So these will be our two groups, growth and gap. And for convenience sake, I'm going to already put them in order from least to greatest, okay? Now obviously when you collect data, they will not appear that way, but as part of our data analysis, we need to arrange them from least to greatest. And so this is, these are the soil respiration numbers for the growth area of the forest. And this is it for the gap area. So in the context of this problem, our null hypothesis is that we would say the growth and gap areas produce similar, or maybe I should not write this. The growth and gap areas have the same, I'll just say have the same population distribution.
Can we only talk about population distribution, or are there other parameters, like not parameters, but other things that we can talk about, or just population distribution?
Yeah, well, for this test, we're just talking about the population distribution. I don't know that many non-parametric tests myself, so I'm sure there are non-parametric tests that try to talk about the spread of a population.
Okay.
But without the use of parameters also. It feels very strange doing non-parametric statistics for myself also.
Is there so general?
Just because I'm used to using symbols for everything, and kind of thinking it's easy to think about the mean of a population and stuff like that, and we don't say that for non-parametric tests. So. All I have to say is, yeah, I don't know.
Okay. But for this test, it would never be anything other than population distribution.
Yeah, we're just talking about population distributions here. Just kind of that. And then the alternative hypothesis, okay. We can have a non-directional or a directional alternative, okay? So non-directional would be the 2 areas have different population distributions, okay? And then the directional alternative, again, should be specified before you look at the data, but perhaps the researchers were saying, well, we're expecting the soil to breathe more in the growth area, okay? And so then we could say, for a directional, we could say the growth area will tend to produce larger values than the gap area. Okay. So we can choose whichever alternative we want, whether it's the directional or non-directional alternative. Okay. And then we'll do the nitty-gritty of the actual test. Okay. And again, we learn things by hand, which can be argued may or may not be useful, but I think there's merit in seeing how these things are done by hand. Okay, so let's. So what we're going to do is we're going to take each number in one column and count how many numbers in the other column are smaller than it. Okay, and so if it were the null hypothesis, if the null hypothesis were true, the first number over here, and here we have two different amounts. I've got 7 values over here and 8 values over here, so it's slightly different. But if I had 8 values over here and 8 values over here, and I went through the process of looking at this first number and counting how many numbers over here are smaller than it. So this number 17, 1, 2, 3, 4, 5, I'm getting 5 numbers in the other column that are smaller than this. And I'm going to continue doing this. If I do this and the null hypothesis were actually true, I would expect, for the first number, only, maybe only one number to be smaller, right? And then, if I go to a number, halfway down the list, I would expect about half of the numbers in the other list to be smaller, okay? And so under the null hypothesis, when I do all of this, we would expect kind of similar counts on both sides for both samples, okay? And when we go through this list, we'll see that's not the case, okay? So I look at 20 and I count how many numbers are smaller. 1, 2, 3, 4, 5, 6. I get 6 numbers that are smaller. I look at 22 and I have 1, 2, 3, 4, 5, 6 numbers that are smaller, and I have a tie at 22. And so when we count how many are smaller in the other list, we award half a point for ties. And so here I will have 6.5. If another 22 were in this list, each 22 would count as half a point. And so I would put 7 there, okay? So at 64, 1, 2, 3, 4, 5, 6, 7, 8, all 8 numbers are smaller. And so for 170, 190, and 315, all 8 numbers are smaller, okay? And so this also illustrates an interesting thing about non-parametric tests. With non-parametric tests, rarely do the values themselves actually matter, okay? Because we're not really making assumptions on the distribution. So this last number could have been 1,000,000 or 1,000 or whatever it might be. It would still only count as 8 points in calculating our test statistic, okay? And okay, so we do this with the other side. So I look at the number 6. How many are smaller in the other column 0. Okay, number 13, 0 values in the other column are smaller. And I have 0 all the way up until I get to 18, where only one number is smaller. At 22, I have 2 numbers that are smaller and one that is tied, so I get 2.5. And at 29, I have 3 values that are smaller. Okay. And I add up the total columns, column totals. I get 6.5 over there. And if I add up all of these numbers, I get 49.5. Okay. So under the null hypothesis, if the null hypothesis were true, I would expect that both of these rankings to be kind of similar across between the two columns, and I would expect kind of the total value to be at least comparable to each other. And here I'm getting something very different. I'm getting 49.5 over here and 6.5 over here. Okay. So we could do. So the step here is count for each value. Count how many values in the other column are smaller. Ties are worth 1/2, 0.5. Okay, and then add up the total of each column. Okay. And our test statistic is the larger of the two columns. Okay, so the larger column, this is our test statistic U. I don't know why it's U, but that's the letter that we use. And there we have it. Okay, so far so good. Okay, and so at this point we go to a table, a reference table, and we look up this value 49.5, and the reference table will convert this test statistic into a p-value. So we use the Wilcoxon Mann-Whitney reference table. Okay, and we look up U equal to 49.5, and then it also matters our sample sizes. So we have n and n prime, and our two sample sizes were 8 and 7. So the larger n becomes n, and the smaller n becomes n prime. So one sample had 7 values, the other sample had 8. And so we assign those to n and n prime, and then we go to our table. Okay, so in our table I go to n, and I go to 8, and n prime I go to 7. So I'm going to look up values in this row right here. Is that okay? Okay, and so with our reference table, I look up 49.5. So if my value was 50, then I would know that my p-value, or tail area, would be equal to 0.0093. And if my value was 48, I would know my area would be 0.021. What I'm getting, however, is 49.5, so I have to say, okay, it's going to be somewhere between 0.021 and 0.0093. Is that okay?
What are the values at the top where n is? What are those equal to?
8 and 7, or?
Sorry, on this side, on the table.
This?
Yeah.
With this? So this is kind of like approximate p-values. It's like if you're looking for something in the 0.01 range, look here. Okay. Is what it's saying. Is because the Wilcoxon Mann-Whitney test, it's not continuous, or the values you get, they're not continuous, because when you add up the ranks, you're either going to get 49 or 50, or maybe 49.5 if you do the half ranks. So you're not going to get 49.2, and you're not going to get 49.7 or anything like that. And so we're not going to have, like on the t-table, we could look up the exact test statistic that would give us 0.01 in the tail. We don't have that over here. The closest thing to 0.01 that we can get is 0.0093, and that test statistic is 50. Okay, and the closest test statistic, in this case, would be 0.0070, and that one is 45 or something like that. So that's what happens. So these are just kind of like, I guess in your head, if you say, I want to have a significance level of 0.01 or something like that, the test statistic you need is what it's saying. Okay, so anyway, so my tail area is between 0.021 and 0.0093. Now, when we started this, I said we could have, two possible alternatives. Do we want the directional one or the non-directional one? Okay, so if it was non-directional, we would just take this value and say, okay, that's my p-value, and it says, so actually this gives an explanation here, and it says the corresponding p-values are for a non-directional alternative. Okay, directional p-values are found by dividing the number in italics in half. So that's what we do. So if we wanted to do a directional alternative, the first thing we need to do is do a directionality check. Okay, and so here it says the growth area will tend to produce larger values than the gap area. We go through the process and we get 49.5 versus 6.5. Okay, so in that case, yes, we might have evidence supporting the idea that the growth produces larger values than the gap. Okay, if I had flipped this around and said the gap area will tend to produce larger values than the growth area, then our data does not support that, and we would stop the test there and say we have no evidence to support this. But
this is an alternative hypothesis.
Yes. So I'm going to write this here. So if HA is non-directional, then our p-value is between 0.021 and 0.0093. If the alternative is directional and directionality is met, okay, our p-value is between 0.021 divided by 2, so 0.0105, and 0.0093 divided by 2 is 0.0045. 465. And that's it for the Wilcoxon Mann-Whitney test. The rest of section 710, it is interesting. It goes into kind of how these numbers in our reference table where they even come from. Okay, and you can kind of do permutations. If you had values, 8 values over here and 7 values over here, and you continue to just mix them up, you can count how often you would get one column having this test statistic and one column having the other test statistic. And that's kind of where these numbers come from. And so the rest of section 710 gets into that. It's interesting if you want to read about it. And again, I think the key here to remember is that this is a non-parametric test. We use it when we have a small sample and outliers are present. Okay, as in this case we had samples of 7 and 8, which are small, and when we look at our growth data, it seems that we've got pretty significant outliers of 315 versus kind of the rest of the values. All right, is that okay? All right, so now we're going to change gears and we're going to cover chapters 9 and 10. And this is all about now inference for categorical data. Okay, so everything that we've covered up until this point has been for numeric data with 1 sample or 2 samples. So in chapters 9 and 10 we talk about categorical data. Next week we'll go back to numeric data. All right, so we're going to start off with binomial data, or not binomial, I should say dichotomous data. Okay. So dichotomous data is kind of like things for binomial situations. Either something, you either have a yes versus no, or something is versus it isn't. Okay. And we will start off with a confidence interval. For the population proportion P. Okay. So imagine having some population. Okay. And in that population, the population could be split into 2 groups, right? Yes versus no. Okay? Whatever it might be. Are you female? Yes versus no. Are you this? Do you have this trait? You know? Are you whatever versus no? Okay? Whatever it might be. That's, this is what we have. And we want to know what percentage is in the population. Okay, what is the population proportion P? Okay, and so because we can't observe the population directly, from the population we draw the sample. Okay, and so our sample has y successes or y yeses. How do you pluralize yes? I don't know.
Yeses.
Yeses? Y-E-S-E-S? Is that?
Yes.
That looks so funny.
An apostrophe perhaps?
Is there an apostrophe?
With no E?
With no E?
No second S? Because of the...
Yes? Okay, well anyway, it doesn't matter, okay? The sample, huh?
I don't know.
Yeah, I don't know either. They always, in Congress, it's the yays versus the nays, right? Okay, so anyway,
That's why.
the sample has y, I'm going to just write successes, and n total observations. Okay, and so your sample proportion is p hat, which is y over n. Okay, and that's simple enough, right? We're going to create a confidence interval for this population proportion p. And there are several methods that exist, okay? And you can look up by, shoot, I don't remember what the article on Wikipedia is. But there's several methods, okay? And so, again, our textbook does something, yeah, just a little bit odd. And I know why. It's a better method. But probably in most other intro stats classes, so if you were to take another stats class, probably the method they will teach you is based on the normal approximation. Okay, so I will write this. So most stats classes will teach confidence intervals for P based on P hat and the normal approximation. Okay. Our textbook uses a slightly better method, okay, a method that produces perhaps more accurate confidence intervals at the expense of just making it a tiny bit more complicated than the normal approximation, okay? And so it uses what's called the Wilson adjusted sample proportion and the Wilson confidence interval, okay? So we have the Wilson, I think it's Edwin Wilson adjusted sample proportion. And confidence interval. Okay. And so instead of calculating p hat, we calculated the Wilson adjusted sample proportion, which is p tilde or p squiggle and we add 2 to the numerator and 4 to the denominator. Okay. And this gives us, when we create confidence intervals based on this, it gives us, slightly better performance. And it also helps us in extreme cases. So let's say you're looking for a rare disease. Okay, how many people have some rare disease? And maybe you survey 100 people and nobody has it. Okay, in that case, your sample proportion is 0. And if your sample proportion is 0 and you use the normal approximation, you end up getting no standard error, and you can't produce any kind of thing. So what the Wilson adjusted sample proportion does is it pretends like you had 2 observations of the, with the disease, but then it also adds 4 to the denominator. Okay, and so that works in the opposite case where, let's say you want to know, how many people have 5 fingers on their hand. The answer is not 100%, but maybe you survey 100 people, and all 100 people said, "Oh yeah, I've got 5 fingers on my right hand." Then in that case, it adds 2 to the numerator but 4 in the denominator, which essentially says there were 2 people that didn't have that.
Like 0.5 and 0.5.
Yeah, so it kind of just adjusts. It takes it off of these extreme bounds of 100% or 0% also. Okay. The 2 and the 4 come from the fact that we're going to make a 95% confidence interval, and for a 95% confidence interval, our critical value would be 1.96, but we just round it off to 2 and work with that. Okay, so our Wilson adjusted sample proportion is this. Our standard error for the Wilson adjusted sample proportion is p tilde times 1 minus p tilde over n plus 4.
What's the sample error for
The standard error for our sample proportion, or adjusted sample
So that
proportion.
would be 4 p tilde. Standard error of p tilde.
Standard error. Yes. Standard. Yeah. I can write a little subscript saying as such. Okay. And our 95% confidence interval for p based on p tilde is p tilde plus or minus 1.96 times the standard error, p tilde. And this is very similar to confidence intervals for for mu based on y bar, right? You put your estimate based on your sample in the middle, plus or minus a critical value times the standard error. Okay. Oops, so yes, we save. So we'll try an example, okay. All right, we want to know what percentage of the population I don't know, will vote for, candidate candidate A, B, C. All right, and so, you know, you survey 220 randomly selected likely voters. Okay, how you did this, I'm not sure, but we'll assume you were able to do that. Okay. And 132 say they will vote for A, B, C, whoever he or she may be. Oops. What did I do? Something happened. Okay. All right, so let's make a for the proportion of all voters in the population. Okay, so in our case, our Wilson adjusted sample proportion is 132 plus 2 divided by 220 plus 4. I get 134 over 224. And that is 0.5982. Okay, and so my standard error is that okay, so let's do this times 1 minus the answer divided by 224. Okay, and so I get 0.00107. Oh, I forgot to take the square root of that. Oops. Okay, I get 0.03275. Or 276. So my confidence interval, 95% CI, says 0.5982 plus or minus 1.96 times 0.03276, which gives me, so I get 0.5982. Huh?
Is that possible? Did I just make wrong? I got a different number.
You got a different number?
Standard error.
What did you get for your standard error?
0.10007.
Okay, let me try this again. Now you could very well be right.
If I'm wrong, I don't know why.
0.5982 times 1 minus 0.5982 divided by 224. And I take the square root of that. I'm getting
You get the
point.
same number again.
Huh?
You get the same number.
I'm getting the same number. Times 1.96. I'm getting
Did we divide by 224?
224.
Or did we divide by that? And we did that just now?
I think.
There it is. I entered it wrong. There we go.
Okay.
I forgot the second two.
All right.
There we go.
Mystery solved.
Sorry.
No problem. Okay. All right, so I got 0.5982 plus 0.0642, 0.6624, and let's change that to a minus, 0.534. So we write, we are confident, we are 95% confident that candidate ABC will win will win between 53.4% and 66.24% of the vote. Okay. So do we have evidence that candidate ABC will win the election? Yes. Okay, because 50% is not in our interval, right? So 50% is not inside our interval. So we have evidence will win the election. I know all the debates and stuff are picking up.
So that value of 50%, is there like a name for that? Because we're kind of comparing our p-value to that. But that's
Not our p-value. Or wait, I'm sorry.
Oh, our confidence interval.
Confidence interval to 50. Well, that's just a majority, right? To
Yeah.
get to
I'm
win
guessing
an
most of these
election.
things probably won't have stuff like that then. Never mind.
All right. Are there any questions on this? Okay, and again, so this is confidence interval for the population proportion P based on a sample using the Wilson adjusted proportion. Okay, we'll take a break here, and we'll come back and we'll do more stuff with categorical